How's everyone doing? All right. Today I'm going to talk a little bit about Android's bootable recovery. So nice to meet you all. I'm Drew. I'm a security consultant for Modisano. I also work on the CyanogenMod Android project. Some of you may be familiar with if you have an Android phone and replace software. I wrote and maintained the technical wiki and exploit database for the CyanogenMod project. I've ported Android recovery to probably 40 or 50 different devices from every OEM out there. My cool guy internet handle is Ukonos, if you want to find me online. So what is this all about? What are we talking about here? So the first thing is, most important, is why do I care about this? What's interesting about Android's bootable recovery? Next, we're going to talk a little bit about the structure and what makes up an Android recovery. We're going to talk a little bit how to device map, so to get a new device and figure out how it works inside. Do a little bit of firmware inspection, and then we're going to talk about how you can use this to build your own. So Android, every Android device out there, tablet, phone, has a built-in mode called recovery, and it's accessible usually with a very strange button combination that you need to hold it when you boot the device. So sometimes we call it the death grip of death. The stock recovery that comes with these devices is pretty useless to us. It's essentially for two main things. The first is installing carrier or OEM over-the-air updates. So, when the new version of Android comes out, your phone says, "Hey, would you like to update?" If you click yes, it reboots into recovery, and you'll see kind of a little progress bar, and then you come back and you have the new version of Android. So that's what most people use the recovery mode for. The other is to repair a broken installation of Android. You may have had to do like a factory reset if your phone is not in a bootable state, which essentially clears out a few file systems and then gets you back to a fresh install as if you had just turned the phone on or the tablet for the first time. Sometimes the stock recovery comes with ADB, and for those who aren't familiar, ADB stands for the Android Debug Bridge, and it's kind of like the Swiss Army knife of Android development. You can get a shell with it, you can push files and pull files off the device with it, you can get log data, all sorts of stuff with that. So this is nice to have. If you don't have it, not all OEMs are that nice and provide you with this in your stock recovery. And as I said, it's pretty limited. It's pretty useless for the hacker. So that leads us to custom recoveries. Custom recoveries provide root access. They provide way more useful binaries via something like BusyBox, where you can kind of have any applet you want, any GNU tool that you're used to. You can package in your recovery. Probably the most important thing if you're modifying or hacking devices is that it allows for a very easy backup of essential firmware. So using a custom recovery, you can back up the stock installation of Android. You can back up your modem, basebands, any bootloaders if you'd like, any essential firmware on the device. It allows a very easy way to back that up. So if you plan on modifying something and you do it wrong, as typically happens when you start hacking on something, it provides a great way to just reset that back to a workable state for you. And in addition to that, what a lot of people use custom recoveries for is scriptable installations of custom Android implementations. So something like CyanogenMod or any of the other open source Android projects, you basically drop this file similar to how your carrier will give you an over-the-air update. You can do the same thing and have total control over what happens. So If you need to format a file system and push a bunch of files at once, it's a handy package just to click go, and it just does everything for you. And these files use a scripting language called Edify, which is pretty readable. It's pretty easy to figure out, and again, very customizable. So here's a look at a Nexus 7 tablet running running a custom recovery. These menu options are customizable if you're compiling your own, so you can make shortcuts for yourself. You can change the operations of what these things do. It's kind of completely in your control in a custom recovery. So why is this significant to us? I kind of explained a little bit why this might be useful to you, but to kind of drill a little bit further, this is the best way to sort of investigate and modify firmware on an Android device. And it's a direct vector for essentially full control over a device. As I said, the custom recoveries provide root access. So if you're able to get one onto a device, you can mount any of Android's file systems as root and modify as you need to. So this is a great level of control that's provided to you. So some potential uses for this, for the hacker scene, penetration testing. This is great for, if you need to modify files on a device, or let's say you can't modify files. So this will allow you to see into like Android's sandbox, for example, into each application's separate sandbox, pull files, modify files in a state where Android's not booted whatsoever. And this, again, is sort of like a standalone bootable Linux environment. So you don't have to worry about breaking something while Android's running. You can kind of do this under the covers, so to speak. It's good for like forensics and data acquisition. So if you're trying to take data off of someone's device or modify data on someone's device, this is a direct vector for that. And in a lot of cases, we'll get into more later when we talk about fastboot mode. It's great for forensics because you can actually boot this without writing it to the device, which is important to not modify it if you're trying to access data that way. It's a vector for bypassing security controls, so all of your PIN codes and your pattern unlocks and all these interesting things like that are stored in the user data partition. So if you can mount that as root, delete those files, you can delete someone's lock screen. You can bypass a lot of Android's built-in security controls via custom recoveries. And again, it's useful for Android testing and development. So if you're building custom versions of Android, you want to test things out, this is a great platform for that. All right, so now that we've talked about that, the important question is, how do I do this? How do I take this and make something for myself? So the steps for that are to map out the device, get the kernel source for your particular device, and build what's called an Android device configuration. And we'll kind of touch on these as I go here, but so I originally got into this because previous to security, I was a Unix system administrator, so it's very familiar to me to work in an environment like this. And thanks for the few laughs at my shitty Jurassic Park joke there. So every device is unique in Android. There's kind of the way that OEMs like Samsung, for example, sell a device, Galaxy S3, Galaxy S4, these things. There's a large number of variations of these. So calling something a Galaxy S4 is useless to us because there's probably 10 variations of that same device that are sold under the same name. Internationally, in the US market, every carrier has their own sort of separate version of that device. And this is something we're seeing getting a lot better now. OEMs, companies are making things more consistent for themselves more than anything. But a couple years ago, I think the Galaxy S2 is probably the best example. There's a ridiculous number of variations of that with totally different partition layouts and So it's very unsafe to assume that the sales name is the best way to identify a device. So we need to figure out how these work. We need to take each phone as a completely different canvas and figure out exactly what makes that unique. So the typical parts of an Android boot image, there's a few large variations of this, but I'll talk about the main ones here, and there's probably There's definitely more types that you'll see in the wild, but this is sort of like the top 3 that you'll see probably 80% of the time. So the standard Android boot image is an initial ramdisk style Linux bootable image. It has a very specific Android boot header that tells the device, yes, this is an Android image. There's a compiled kernel, and there's also an initial ramdisk stored in a couple different varieties that you might see. But the next style, this is something that was much more popular a few years ago when device space was limited and internal memory was more expensive then. This, you see an init ramfs style, which means that instead of having a separate ramdisk kernel image and header component, the ramdisk is baked into the kernel at compile time. So typically, these are on one single partition, and so what a lot of companies would do is throw all of the recovery tools into the kernel partition, and you have to share that one spot. So this is actually kind of traditionally against the whole point of recovery mode, because you're supposed to be able to modify all the different components without impacting others. So in this particular case, if you flash a wrong kernel to your phone, recovery is useless. You can't access it. It's broken. So this is something we're really glad they're not really doing anymore. But Samsung did this up until the Galaxy S3. Almost all of their devices had this kind of wonky format like this. And then the third type, this is something that is pretty unique to Sony phones. It's the same idea as the init ramfs in that it's sharing one partition. However, this is more the traditional boot image that you might be used to on the majority of devices. So here's a look at the most common. This is the Initrd style boot image. This is the boot header, kernel, ramdisk, and second stage, which is not used very commonly, maybe in the future, but not currently. And then we sort of have a breakdown of the parts of the boot header on the right-hand side here. So I've called out 10 and 11 here specifically as a point of interest. More modern Android devices, you're starting to see kind of a blob, like a proprietary blob of data inserted into the image called a DTB, which stands for device tree binary. And this is kind of a push on the part of making things consistent for manufacturers so that they can have one kernel and all the changes they used to have to make and have all these different variations they can do in this DTB file instead. And so the kernel is consistent, but the DTB is what changes, and that's just wedged into the boot image at compile time. So it's something that's 2013 and to the future, you'll see this pretty much consistently across the major players in the Android scene. In the initial ramdisk or the ramfs, if you're familiar with the Linux boot images, it loads a temporary root file system into memory. This is completely isolated from the core of Android. Files needed specifically for recovery mode to function properly exist in this ramdisk. It's very minimal. It's meant to be sort of written to very small partition spaces, so you don't see a lot of things in the stock especially. But when we make our own, this is where we can put the tools that we want to work with. Inside here of particular interest is a init binary, which is included in the ramdisk, as well as init scripts that are executed by that binary. And these scripts do lots of different, very interesting things, and there's a whole section that I'll talk about more on that, but just to give you a sort of a preview of what to look for there. And these can be rebuilt or modified to include more tools, extend functionality. So technically, you don't have to compile this from source if you don't want to. There are tools available to take one, rip apart the parts, let you modify it, and then reassemble it. This is something that's kind of hacky, and I typically avoid if at all possible, but not all OEMs provide kernel source like they should, especially in like the Chinese market. It's very hard to locate the source code. So that's kind of your only option sometimes. Other files in the ramdisk. If you're familiar at all with Linux, etc fstab, it's a very exact same idea in Android recovery. Previous to Android 4.2.2, this file is almost always called recovery.fstab. And of course, it maps the block devices to the mount points and lets you specify file system options and that sort of thing. This is almost always found in the etc folder within the ramdisk. However, some manufacturers put this in res for some reason. You see a lot of really strange things when you start to look at these things, so don't expect consistency, I suppose. And then the newer style, after and including Android 4.3, you've seen a push to move to a different style of fstab, and this is called fstab.platform. So you might see fstab.qualcomm or QCOM. It might be named after the SoC itself, so fstab.msm8974, for example, for the Snapdragon 800 series. Only real interesting thing is that the order of the pieces of information is different. So you just need to make it look like the one you're taking apart, and you'll be fine. There's really no variation other than that. So let's talk a little bit about how to device map. So I call this sort of casing a device. So I'd like to take something and not look at anything online, or I'd like to look at it manually and try and figure it out that way first. So a good source to do this, of course, is the stock firmware, because you can extract this information pretty cleanly if you are able to access the stock firmware. There's lots of websites online where you can download stock images from like HTC or Samsung or Motorola or whatever the case might be. And if you can get these files, it's a huge win, because you can just take them apart and figure it out from that. Sometimes you're not so lucky, though. So you can use old friend like DD to pull these images manually off your device if you have root access, and then begin to investigate them that way. The primary uses of this, as I said, are sort of like recon, figuring out how the device works, and also troubleshooting, because as I'll talk about in a little bit, there's a lot of really squirrely like OEM hacks that you see, like stuff that's just really bizarre and broken, that if you're building this and you don't emulate that, it won't work. So it's good for figuring out when people do like really weird things in the ramdisk. And of course, the device topology. Kernel source. So as I mentioned, you can kind of get by without this sometimes. On the init ramfs style, you absolutely have to have this, because you're not able to repack that as easily, because you need to compile the ramdisk into the kernel. The other really great thing about having kernel source is making the image smaller. So especially on the older devices that have very little space for recovery, as low as 5 megabytes sometimes, you can kind of clean out the kernel def config to make your outputted Z image much smaller, to cut out things that are completely useless to you in recovery, like wireless drivers and stuff, for example. You don't need. The other useful thing about having the kernel source is that you can modify this to do anything you want. So if you're trying to test something from the stock Android implementation's kernel, you can emulate that directly in the recovery and make changes to it if you need to. So kind of a little anecdote about this. Samsung had a SoC, they still do, a processor called Exynos. This was very popular with the first Galaxy S2 and the first Galaxy Note. And they made a lot of really dumb mistakes in the dev portion of the kernel. They left a device world readable and writable that allowed direct physical access to memory on the phone. So this is a great place to sort of boot the kernel in recovery and poke around and see, oh, this looks interesting. I'm going to remember this and maybe attack it in the booted Android version. But it gives you a great way to just kind of quickly move around the kernel and see where somebody might have made silly mistakes like this. The other important file we need is called the build.prop. The most important thing we need from this is the code name of the device or the board name. And this is sort of going back to what I was saying, there's like 10 or 15 variations of Galaxy. Like that doesn't mean anything to you. What's interesting is the board name. And this is the only way to uniquely identify a device. So that is called out specifically in the build.prop file. We need this to build our own device configuration. So this is very important to write down. If they're nice, they've left you a eMMC or MTD file in the proc file system. Most modern devices use eMMC storage, so I would definitely look for this first because this will give you a direct mapping of partition to what file system lives there or what firmware or whatever lives there. A lot of times you won't see this, so you need to kind of make this yourself. So a good tool for that is to dump out proc partitions because it will give you block sizes, and you can use that to sort of like cleverly figure out what's stored where because it's not going to be multiple gigabytes provided to you for recovery or another boot image. So look for things that are small enough and then extract those and investigate them manually. And the config.gz is very useful if the OEM does not provide you a handy def config for compiling the kernel, which you can use with something like ikconfig to extract that and use the exact def config that they did. You're seeing a lot less of these days for security precautions, so they may exist. Look for them, I suppose. All right, so where do we find all this stuff? Let's take a look at taking apart some of these images real quick. So here's a dump of a recovery from a phone called the HTC Droid DNA. This was a Verizon, a US carrier phone. And here we can see the Android boot header I mentioned earlier at the very top, and then the kernel command line, the boot command line is called out here in this image. So if you're DDing random partitions off the device to investigate them manually, and you see something like this, you've found a bootable image. So either the kernel or the recovery. It's a very safe bet that that's what you found here. There's a couple tools that are popular for this kind of work. Unpack boot image, and at the end, I'll provide source code references. So remember these numbers when you go back and reference the slides, and you can get the source code for these tools. Unpack boot image, the usage is pretty easy here. You see, it takes an input image and an output directory, and then you use zcat to dump the ramdisk to CPIO and explode it out, and then investigate it that way. More modern tool, probably supports the most types of firmware, is called makeboot. And you can see similar usage there. This will kind of do everything for you in one punch, so it's pretty handy. And then we have the unpack init ramfs shell script that people have written, and this will help you extract the ramdisk out of a compiled Z image from something like an earlier Samsung devices. And then failing these tools, good old bin walk is a great way, combined with DD, to take specific pieces out of an image and extract them that way. So here's a quick look at makeboot. This is against the Galaxy Note 3 recovery image. And I've kind of highlighted the more interesting pieces for when you're trying to build this yourself. You absolutely have to get the kernel page size properly. This is almost always 2048. HTC is very fond of 4096, so if you don't specify this right, it won't boot. And some sort of oddball Chinese OEMs use like 16384 here, just madness. So the ramdisk offset is extremely important. This is almost always why, if you're building one of these yourself, it won't boot, because you haven't offset the ramdisk properly. And this becomes much more important on newer devices that have much larger partitions that you're not necessarily filling out all the way. So you need to note this down. And then, of course, kernel command line we saw earlier, and the DTB file is also extracted for use with reattaching to your image. So our goal here is to get the ramdisk and a working pre-built kernel. The pre-built kernel is useful for building these if you don't have source, but also for having a guaranteed working environment. You know this kernel boots on the phone. So if, it takes a lot of the guesswork out of things if you know that the Z image is proper, because it's, you took it off the phone. And it helps you kind of narrow down where something might be broken if you're doing this yourself. Again, I sort of mentioned init scripts, custom scripts in here we want. And this is a great vector for finding a way to root a device as well. So why are these init scripts so important? These are an amazing source for bugs, for very sloppy code, for very, old school symlink attacks are still alive and well in a lot of these files. Overly permissive files and directories, that sort of stuff. And debug functionalities is exposed in these files as well. So these are an incredible source to find information. And it also shows what services are running, what their users are, and when they should run at what time of boot. So this is important to know if you're trying to make your own, how to emulate behavior that you see here. So we'll take a look at a couple silly things you might find in some ramdisk init scripts. This is provided with kind permission from Just In Case, a friend of mine who's kind of big in the Android root scene. So here we see a directory created way too permissively. We also see a file that's too permissive as well. It's world readable, writable, executable. So what can we do with something like that? What's interesting specifically about mid.txt, for example? So this may be a little hard to read here. This is very common in older devices that this attack still works perfectly. You can, since you're able to write to mid.txt, you can back it up, create your own, and then symlink it to something like uEvent helper, which will execute whatever is in mid.txt as root when run. So we see here that we've got our root script. We're echoing that to this overly permissive symlink, which when executed will execute in the context as root. So you have a direct vector to root a device with something like this. Another example, again, here we see a directory, Etsy recovery, which is far too permissive and makes no sense to be 777, but you find this stuff all the time in init scripts. And a log file with 666 permissions. So kind of a similar idea as the last one. Delete the log file, symlink it again. Here, particularly, Android, when specified with this ro.kernel.qemu parameter, will tell Android, hey, I'm running in an emulator, so ADB should run as root. So if we can force a reboot of ADB and set this parameter, when ADB comes back up, it thinks it's running in the Android emulator, and you'll essentially have a temporary root shell on the device, which you can use to do whatever you want and go further with it. So what else is interesting in the ramdisk? We talked a little bit about init scripts, but what else is in there? A lot of times you see what's called like a watchdog daemon. This is something that needs to bark every couple seconds. Sometimes it's 30, sometimes it's 5 minutes. But if that doesn't happen, the kernel will just shut down and the device will shut down. So if they're doing something like this, you absolutely need to replicate this daemon in your custom recovery and set the exact timeout, or otherwise you'll be working on something and the phone will just shut off and you'll be like, what the hell, what happened? Other times you'll find necessary kernel objects in here. The most famous probably of this is a chip maker called Rockchip, and they just make insane decisions when they're building Android devices. But they decided to try and write their own flash translation layer to run ext4 on top of an MTB flash device. And so without these kernel objects, you can't even mount storage, period, in recovery. It's just totally useless to you. So you have to do some kind of ugly hacks and fudge the version magic to get these to load properly. Otherwise, you're screwed. There are also some interesting standalone binaries in here that, maybe you can poke at those. Who knows? All of these are totally different, so you'll run into some weird things like that. And of course, some special commands are available. A lot of times, the device will have what's called a miscellaneous partition, or MISC. You'll see sometimes called out. And this is kind of a low-budget way to send messages between stock Android to the bootloader and back and forth. So, for example, you can write the string reboot-recovery to the miscellaneous partition, and the next time the phone boots, the bootloader will see that and know that you're supposed to drop you into recovery, or maybe drop you into the bootloader directly. But your custom recovery might not know that it's supposed to clear that out, so you can get stuck in a weird reboot loop where that string is never cleared, and it's stuck in this sort of loop that, oh, I'm supposed to boot recovery. Oh, I'm supposed to boot recovery over and over and over again. So this is something to look for and clear out manually. Set something on your own scripts to delete that safely so that you can kind of get back to your working phone there. So, what if I can't figure something out? What if I don't have stock firmware? There's a lot of possibilities when you're looking at all these different devices. Attempt to do this by hand with ADB shell. The output of mount is very useful because it will identify at least 3 or 4 of the necessary partitions you need to make the stuff work. And again, I sort of mentioned how you can use proc partitions to make some educated guesses on where the stuff might exist. So let's talk about building one of these. We need to build what's called a device configuration. So Google decided to make this like a meal ordering concept, like you might see a big menu in a restaurant, and combo meal, I want number 5 with a Coke and fries, sort of thing. So every device config is what we call like a combo. It's a combo meal. And these combos can inherit from one another. So going back again to like the Galaxy S3 example, there might be 10 variations of that, but we can share sort of a common combo and then make our changes in separate sub-combos. So it's important to know that these can inherit from one another, and you might need to look elsewhere for necessary files. And what we're trying to do is build a new combo. We're adding your favorite sandwich to this menu now. So how do we build this device config? Of course, you can use the signage and mod source. You can use the Android open source project source. You can, anything you want, really. There's a lot of different projects out there accomplish the same goals, really. You need to get source code for this. You need a Linux or OS X box to do this sort of stuff. You'll drive yourself crazy trying to do this in Cygwin and Windows. It's just don't even do it. It's dumb. And of course, all the info that we've talked about here, how do we gather this? Now we know. Now we need to plug it into our company. So there's a handy script available in AOSP and then CyanogenMod source called make vendor. You don't need this, but it's great because it kind of does everything for you in one bang. It gives you a nice bare bones config. And it takes 3 parameters. The first one you see, of course, Samsung is the OEM name. This could be HTC, Motorola, anyone, Sony. The second is the board name we talked about, the specific code name for that device. We need to be consistent in how we call this. So once we figure that out, call it there. And then the last parameter is any bootable firmware from the phone. This could be the kernel. This could be a recovery. This is important to have because it sort of takes it apart for you, makes a skeleton config. And here we can kind of see, again, the Droid DNA. I've marked the files that are created by make vendor with an X. So if you don't have access to the script, you can sort of emulate this yourself. These are the bare minimum that you need to compile recovery. And I'm sure you'll notice there's lots of other files in here. These are things that you have to do to make it work. So for example, these init scripts, I took from a stock recovery because this won't work without that. So it depends totally. Each phone, again, is just sort of its unique snowflake. You need to figure out what it wants, or you'll have a non-booting device. Make vendor is pretty terrible. It's almost always wrong, but it does give you the shell files you need, or the base files, in other words. So it gives you the base files you need to work from. It's a good jumping in point. These three files in particular are pretty crucial to building a custom recovery, and I'll talk about each one of them quickly here. The board config is probably the most important file here. This is a continuously evolving make file. All the parameters about the internals of the device, the SOC, ramdisk offsets, all those sort of things are stored in the board recovery. It requires the most modification, and for the scope of this talk, we're only going to cover like the bare things needed for recovery. But if you're building a full Android implementation, this file is crucial, and it gets very large the more you work on it. Of particular note here, we talked a little bit about forcing a ramdisk offset because otherwise it can't find it at boot time. These are two parameters. The first one is largely deprecated after Android 4.1. You'll see in the make boot args is the current one now. Use this to specify your offsets. The device codename makefile is specific instructions on what needs to be inserted into your output ramdisk and where they should go. So if you need to take a watchdog daemon, for example, from the stock phone, this file will say, OK, here's where it is in the combo, in the device config. Here's where it needs to be after compile time. And this is essential for replicating terrible OEM hacks. This is the best way to do that. So then we use launch to load our new device combo. This is how to load in. And so it sets all your environment variables, it sets the compile options, and then you can make something like a recovery image. So the make target varies. Recovery image will build you the most standard initial ramdisk image. There's other types you might see, and sort of outside the scope of this, but read the make files. So test it. Before you even begin to try and boot or flash this on your device, take it apart with the tools we looked at earlier. Make sure that it looks like the stock one, because if you made a mistake there, it's easy to catch, and it'll prevent a scenario where you flash something non-bootable to your phone and potentially put yourself in a bad position. And of course, make sure it fits, because if you're stuffing a lot of custom tools into these things, it might go past the partition boundary, so make sure that it's actually going to fit before you try and flash it. Because you'll have some bad news otherwise if you don't. So now you need to flash it. You can use DD, which requires root, of course, and wink, wink, see the init portion that we just talked about. We won't really cover flash image too much. Particular note, Samsung has a very specific bootloader, which has tools that you need to talk to it. And we'll talk a little bit about ODIN and Heimdall, and also fastboot. So how many people have a Samsung tablet or phone? Raise their hands. Now put them down if you've heard of download mode before. OK, so you may want to pay attention a little bit to this guy. This is a mode that is on pretty much all of their devices, especially internationally. There's only a few exceptions for US carrier models. And this is a direct, very permissive bootloader that you can't do anything about, and allows raw images to be flashed directly to the device. Internally, Samsung uses a tool called ODIN to do this. Unfortunately, this is a Windows-only tool. It's closed source, and it's probably the worst piece of software I've seen in recent memory. Here's a look at it. Sometimes you need it, sometimes you don't, but most preferably don't use this unless you have to. ODIN requires a U-star formatted tar archive, which is kind of interesting because there's no quick and easy way to do this in Windows, which is what their tool only runs in. But here's how to make one. U-star formatted tar archive, and then attach an MD5 sum of your tar archive to it. A lot of versions of ODIN will not even attempt to flash unless it sees the checksum checks out. Not all of them do, but it's, it's easy to do anyway because it will always work. So the other interesting thing to note about ODIN is that the image has to be named exactly like the partition itself. They use something called a PIT, a PIT, which stands for Partition Information Table. And this has the mapping of which MMC block partition and what its safe label is called. So sometimes recovery needs to be capital letters. Sometimes it doesn't. Again, there's very little consistency here. So if it's not named exactly, ODIN will just puke on you. So let's talk about Heimdall, which of course is cross-platform, open source. We like this. And it's capable of writing raw images to the phone instead of this goofy tar archive. Much more flexible than ODIN and has a lot more features. So what's wrong with this? It should be pretty obvious. If you lose physical access to your device, I can boot it into this download mode and flash whatever the hell I want to your phone. And so it's easy for me to build a custom recovery for your phone or find one that someone's already done online, boot it, mount your user data partition, and do whatever I want. However, this is where user data encryption is very useful to you because that will sort of mitigate this possibility. I won't be able to mount an encrypted file system, but I will still be able to modify your system or your kernel potentially using this vector. There are a lot of newer protections, but they're very inconsistently applied. So this is still a very active problem for them. Talk quickly about fastboot mode. This is found more commonly on lots of different devices with lots of different implementations. Your Nexus, your HTC phones, your Sony phones, Motorola in some cases will allow fastboot mode. This is a lot of cases, this is a great way to test an image without actually having to flash it to the device. Fastboot supports a command called boot, which will download the image from your PC into the phone's memory and boot it once. So if you need to quickly boot something, this is a possible way to do that. Not all fastboot implementations support boot, and especially if the bootloader is locked, that is not a possibility. And most times when you unlock the bootloader, it will responsibly erase your user data partition to prevent accessing personal data, unless they make mistakes. So here are a couple CVEs from this year. The first one, they just completely forgot to check at all if you're able to use the boot command. So you can, it doesn't even look at the locked status. This is in some implementations of little kernel that you might see out in the wild. The second is a little bit trickier to work with. It's a way to sort of like spoof your own signature on a device using the RSA QBroot attack. And I suggest you read the CVE because it's a pretty complicated setup to get this to work. But it just proves that there's ways around a locked bootloader. There's ways to use fastboot beyond the way it was intended to sort of test and flash these things on your own. So newer protections, we'll talk a little bit about this. They're coming, they're realizing that this is really terrible. So in Android Lollipop, they've moved init to run their own context. So it will not execute as root like you think it will. Newer protections like Samsung's Knox and Secure Boot are becoming more common. And of course, they've ratcheted SE Linux up to 11 in the new version of Android Lollipop. The full extent remains to be seen. All we have now are developer previews. So some common issues real quick. I'm running short on time here. If it boots on the first try, you're incredibly lucky. This is not common. So again, sort of check the ramdisk offset, make sure init isn't misconfigured, make sure you're emulating some weird OEM hack, and make sure that the DTB file exists and that it's offset properly. And this image is kind of what you have to do sometimes, just bang on the keyboard until it works, right? So if you want to get started with this, GitHub is lovely for this. You can search for work people have already done on this, take what they've done and work with it. Again, a lot of hosts, a lot of websites have stock firmware that you can get started with. First one's for Samsung hardware. XDA developers, of course, is very popular for mobile. And sites like RootsWiki also exist. Set up your build environment, there's guides for this all over the internet. I won't talk too much about them. And review the links in my references section. So read this in your own time. And here's some contact info. If you're looking to get started with this, reach out to me if you run into problems. Like, I'm always online to help you. And I also want to mention the DroidSec community on IRC is great for your Android security. So thank you guys very much for your time.
Muchas gracias, Drew.